Yeah, so thank you very much for the introduction. I already gave away too much of the talk, I think, beforehand. So the genesis of this talk is a keynote I was invited to give at the Charité a few months ago. And it was kind of a closed group. It was a large room, but it was a closed group. And so this is an opportunity to share it with the rest of you and to share it with the rest of the community. The basic idea is looking at these two schools, particularly at the machine learning one because of the hype around it at the moment. I have worked in both schools, which is unusual. And, well, we'll see what we can learn today. But the specific issue here is about healthcare. And we've had two very interesting talks already in this session about biological applications. And healthcare has issues around it when it comes to data. And I'm not even talking about the privacy issue, which mean that often these approaches are more and less appropriate in different circumstances. So the first thing is, what are the buzzwords that we're talking about? So AI, I promoted the talk as AI in healthcare because that's what you have to do in Berlin at the moment, especially if you're looking for funding, which I am on a separate project. We're not talking about generalized AI today. But you have to understand that there is such a thing, and you have to understand that AI means many things to different people. And so that's why I stay away from the word in the rest of the talk, I hope. That said, I mean, I'm a little bit loose with the language, and if anyone's confused about when I say big data or machine learning, sometimes it is to fit it on the slide. The point is hopefully clear, but if it's not, ask me and we can clarify things. The biggest use of these tools today in medicine and in healthcare is actually in computer-aided decision-making. And I'll show you some examples of that in a minute. But this is really where the computer is as a support tool for the doctors in their practice, in their clinical practice. Doctors have an awful lot of decisions to make on a daily basis. And it's been shown time and time again that you're better at your decision-making early in the day, early in your day, basically. And so whenever they start their shift, they make less mistakes. And as the shift goes on, the decision of whether they want another cup of coffee becomes quite mentally intense. And I mean, many of us have worked in difficult jobs, and we can all somehow translate that. But in their job, it's particularly difficult also because there's always the idea the patient may die. Okay. So machine learning, largely today we're talking about deep neural networks of some kind, convolutional networks. I'm going to refer to it as big data approaches in the talk. I understand what big is, but we can discuss it after or whatever. The other approach is the mathematical approach. So the mathematical approach is really about bespoke models, statistical models of data sets. Put an equation here just to show that I'm really into math. And then the final thing is something that's new and coming now, and which is called a hybrid model, where you try to take the best of these approaches. So as far as I can see in academia, this is not really a thing. You'll often have a student with a background in one of the techniques operating in the lab that specializes in the other, so they're trying to use that technique on the same problem set. But there's rarely a case where a single convergent outcome comes from a mixing of the two models. But we're beginning to see it, and there's an example of a company here in Berlin that are doing it. So let's start with the pure machine learning approach. So before Christmas, Andrew Ng's group over in Stanford published this paper excuse me, on the archive. And basically, it's a machine learning model. It's a convolutional neural network that looks at radiographies and is better able to diagnose and identify pneumonia as clinicians are. And so this is the cutting edge of actually applying this in the real world. And this is an example which is only an academic example, and it may well be tweaked to infinity in order to get it to work perfectly. But it is an idea where you can hopefully apply this now in other hospitals around the world. And you can try to take an engineering approach now and roll it out. And this removes some of the heavy lifting from the doctors. Some. This example came from last week. It's not so important to read it, but it was 3 or 4 days ago. Chinese AI beats 15 doctors in tumor diagnosis competition. So they're looking at different types of tumor now. And the AI, they've basically trained in multiple of these convolutional networks And each one is specialized on a specific type of imagery and how to identify the tumor from that type of imagery. And then the combined system basically selects which model should be used for this particular data set and puts it through it and quickly makes a prediction. And certainly in their metrics, roughly speaking, it's on the level of an expert, it's of a human expert, which is not completely confusing because it's usually a human who's training the data in the first place, who does the training data. But they have wonderful metrics of how it's so much faster than a human being. It's 2 to 3 times faster than the human experts and so on. So for me, big data approaches, I think they're methods for finding statistical correlations in high-dimensional data sets, and you take advantage of a large sample size. So that's, roughly speaking, my definition here. And that's where I'm going with the main part of the talk. So what I want to talk about now are some of the limitations of using these kind of approaches on healthcare data sets. So I've shown you now the examples of the imagery where it's extremely powerful and useful, but why is it not always so useful? So the first thing is that the users, and by that I mean the mathematicians, the machine learners, the scientists, in practice they often mistake N and D. So N here is the number of data points and D is the dimensionality. In biology, when we think about it, D is often very high, but then it's not necessarily informative. So you can record 10,000 different things from my body, you can attach sensors all over, but usually, if from any kind of modeling point of view, you're not adding much data when you're adding sensors. And most of the sensors in biology are typically sensors where it's the easiest thing that you can clip onto. And really, you're trying to use it as a proxy for an underlying process which has been explored for 30 years in the lab, but you're doing some kind of linear readout. The example that I gave this winter is that we had a flu epidemic here in Berlin, which was particularly severe. And at one point in that flu epidemic, if you went to your doctor and you said, I have a fever, they were already basically saying, yeah, influenza for sure. What's it going to add when they start measuring blood pressure? They actually measure your temperature. They look at your sweat, so your sweat response on your skin and all these other things. Heart rate also is elevated during influenza. They didn't need to measure those in the case of most of the people. And in terms of blood samples, forget about it. That was early in the epidemic before it really got so prevalent here in Berlin. The other thing is N is severely restricted in biology, and this is much less obvious. You kind of think when you're trained into machine learning that just turn around the problem to a problem of gathering data, and then we'll engineer a solution to that. And that's the general approach in machine learning. So machine learning is extremely powerful at doing its thing, and we just need to get enough N in there. Well, that works when you're dealing with traffic to a website. You can get a lot of traffic. It even works with genomic stuff, because you can now sequence an awful lot of genome data. Also, we don't know what the genome data really does structurally, so it's quite hard to do anything that's non-statistical with it. But ultimately, in biology, the N I'm typically used to dealing with when I work in lab cooperations is between 3 and 13. 3 to 13 data points. So that's really in the bespoke modeling domain. And that's where they're working in a lab and they have to do experiments, and it takes them a week to get a single data point. So I have friends who have PhDs in experimental biology where they gathered data every day for 5 years, and at the end they had 2 papers, each of which had N equals 5. And this is a success. This is a big success. And please, this is not to disparage them. It's to highlight the difficulty of gathering biological data. So, but the issue that sometimes is mistaken here is that imagine we're taking my blood pressure every 20 minutes for the next 2 weeks. That's an awful lot of data in one sense. But let's be honest, for most applications, that's a single time series. So that's N equals 1. So to get a population of 1 million people with that kind of sampling is much more difficult. You can't say that each one of those individual independent recordings is an individual data point, because they're not independent. They're from my body. They were taken 20 minutes apart. There's a strong structure underneath them. So unless you're looking to make a model of my blood pressure and you just need a very, very long-term recording from me, this is not something where you can scale it easily. And it's often, we often see this in practice when you get a PhD student or a master's student working on a project. The first thing you do is you typically lump all the data in together, and it's only afterwards that you begin to think, oh, yeah, okay, well, those ones, that's actually the same data. And actually, so those recordings over 2 weeks from me are actually a high-dimensional data set rather than multiple recordings. So that's the first limitation in biology. The second one is a statistical limitation. So I would assume that many people in this room are familiar with this website of spurious correlations. So the one I chose out, which is random on the day that I went to the website, was there's a very, very strong correlation between US spending in science, space, and technology and suicides by hanging, strangulation, and suffocation. It looks very, very convincing to me, I have to say. But, you know, I think we're all grown up enough to know that in repeated testing in high dimensions, you will always find correlations. In fact, as someone who trained in statistics originally, you would be really worried if you don't. So it's really, you need them to be there. But then what are you trying to extract from this? So let's move on. The third limitation is one that I call a limitation of ideology. And this again is, we're still looking here at the machine learning, the big data approaches. So these approaches have a historical preference for model-free approaches. It comes out of their origin in the 80s and 90s. It comes out of what people were thinking about in computer science at the time. They are wonderful, wonderful techniques when you don't know anything about the data. But when you begin to know stuff about the data, sometimes there are better approaches. So biology, by contrast, is largely deterministic. It has many, many unknowns. We'll probably never know everything about biology, but it is deterministic as far as we know. And so why are we ignoring the known mechanisms in biology? And if we go a little bit deeper into that question, biological data is often very noisy. It's extremely noisy. I worked with an experimentalist a couple of years ago where they were teaching students, and the result was how well the students learned on a particular visual task. And he told me, if we don't have one student in the group who actually gets worse, then we know that somebody has faked the data set. So that's how ridiculously noisy this kind of thing is, that one of they see a strong trend for learning for 6 students, and the 7th one just gets worse, and they can't figure out why. It may be an attentional issue. There's many things in the field, but who cares? By contrast, if you build mechanistic knowledge, so a model, into a statistical fit, it improves the signal-to-noise ratio enormously. And that's something you should be looking for. When you've got low N and you've got a noisy data set, you need to reduce the signal-to-noise ratio. And so that's where some kind of model-based approach is more appropriate. The fourth limitation is one of generalization. So I've been a bit cheeky with the English here. I have an American spelling and a British spelling. And the machine learning papers are written with the American spelling, so generalization with a Z. So in these approaches, generalization refers to the ability to treat statistically identical data. And that's really important. This has a very, very strong foundation in statistics, this field. And it's for identical data sets. So when you hold out data to do a trial later on to validate whatever you trained, whatever model you trained, there is an inbuilt assumption that the holdout data is statistically identical to the data that was left behind for the training set. And if it's not, you're in trouble. And this is why there was leave one out analysis and all these kind of things in the early days before we were able to scale up so much. So what happens if you've got an outlier that's outside the training data, which is extremely common in biology? You're not going to gather enough data to fully constrain your problem. There is no way of knowing where it's going to be predicted, where the output is going to be predicted. And the network is not going to tell you that this is not something I've seen before. It doesn't have an input filter that says, hey, this is kind of weird. Maybe you should look at it yourself. The other issue, which is slightly more technical, is that for data sets, even within the statistical training data, it's not clear, and I know there was a talk earlier about training a manifold, but it's not clear that you're actually on a smoothly differentiable manifold. So it's not clear that when you have a second point that's right beside the first training point, that it's actually going to be smoothly predicted to being quite neighboring in the output until you hit a nonlinearity. With most of our modern techniques, it's reasonably okay, but it's really not clear. If you do infinite training data, then it's fine, but it's until you get to infinity, you may have a problem here. And the final issue is one of insight, and this was mentioned in one of the previous talks, but experimentalists, biologists, and medics, they want to know about mechanism. And so these classification techniques don't really teach you much about mechanism. So they may tell you to take the blue pill in the morning, but they won't tell you why to take it. They won't tell you what the blue pill does to your body. They just say, take it, yes or no. So they provide no insight. So just a quick summary, that in practice, the users often mistake the N and the D in this. So the N is the number of data points and the D is the dimensionality of the data. In repeated testing in high D, you will always find correlations, at least you should. Big data techniques historically have this ideological preference for model-free approaches. And this issue of generalization, both outside the data set, but even within it, could potentially be an issue for these approaches. And finally, from a healthcare point of view, yes, we want to make things better, faster. We want the black box, just throw it at it and solve our problem today. But on the other hand, we have regulatory requirements, we have our own intuitions, and so mechanism is actually very important to us. And honestly, you know, I'm in one of the privileged groups here when it comes to training these statistical models. I'm middle-aged, I'm white, I'm from Northwestern Europe. This is the training data for these models when it comes to healthcare. Everybody else is outside that population. And if you have some kind of rare genetic trait, or even a very common one that just happens to exist in a different part of the world, you are less well treated by these models today. And we can pay to enroll more people in the studies in order to get better background, better coverage. But I mean, you're not. There's only 8 billion people on the planet, and it will be difficult to get that kind of training data. Okay, so the first solution in my life was to move away from machine learning approaches and take pure modeling approaches instead. This is something I worked on back about 15 years ago. So this is a sports science issue for fitness testing. And you don't have to understand it, but the basic idea is that you take a blood sample from an athlete at every workload, and you look at what the blood lactate concentration is. And at some point, the blood lactate concentration shoots up. So instead of following what's almost a flat line, it suddenly goes what we would call exponential. And at the time, they were doing this analysis on paper. A coach or a scientist would get the raw data and plot it on graphs, and each one had his own method of analyzing it. They all had roughly the same concept of what they were looking for, but in practice, even for the same coach, he would do it differently over time. So we mathematized it using a number of different approaches, and then we automated it as well. And so the software for this is now used in sports science labs throughout the world. And it's basically the help that a mathematician can give in this applied biological world. It's very simple mathematically. The ultimate answer for the best way to find the turning point is probably going to be the second derivative of a line through here, of a curved line. But we went with other ones as well. We went with all of the ones they had nominally, and we formalized them precisely how you calculate them, so they're completely reproducible. But basically their idea was that this is flat and this is curved, and somewhere around here we want to reliably be able to predict. And so that is now possible using these kind of approaches. But it's very bespoke. It's very, very bespoke. It's kind of like the work earlier on the neonatal breathing. It's extremely targeted to one application. I'd say his application is better than this one, but it's a one that people have an interest in, and therefore you do it. If we go up the hierarchy of difficulty, this is tied in more to Andre's work. So these are neuronal recordings from rats. And basically, using a set of equations, you can describe this behavior very easily. So you stick an electrode in a neuron and you record the voltage from it over time, and you see these kind of patterns of spiking behavior, so of electrical behavior. And so we can fit them very well. It's an optimization problem on an equation that looks roughly like this. And we do it for experiments, and the current process is that per experiment you refit it. And since labs have different setups, you fit data from different labs separately. And if we go up the last step in the hierarchy, we can go and do massive simulations of hundreds of thousands of neurons, and we can do it quite reliably. So this is 1,000 neurons doing activity over time. This is the rough population frequency. It's very tight, around 1 hertz. And there's a bunch of complicated physics we can use, which can actually set up this network so that it fires at this frequency, and so that the average behavior of all of the neurons in the network is that frequency. And we can even tailor what the variance is around that. But most labs I know of in the world, including the most advanced ones, are not doing this. They're doing trial and error on this at the moment. So they're literally just tweaking the parameters until they get to the right place. So what's wrong with these pure modeling approaches? The first is that they scale very badly. You need someone with a lot of experience to come and do it. And you have to trust that they did it correctly, because you can't afford to hire 2 of them. Also, their own career is not completely aligned with this. They ultimately want to be hired as someone important, and they come to your project for 3 to 9 months, and then they leave. And this is quite a strange career trajectory for them. It's extremely laborious and time-consuming to fit these things, particularly the second one with the neuronal models, the neuronal spiking models. And when you try to couple these systems together, because they've been designed separately, they tend not to work together. So you get 2 different neurons that have been fitted in the same lab, you get the same person doing the experiments, and yet through a little bit of random variance and a lot of bad luck, although it's the main thing that you see, the 2 models don't fit very well together. And you say, oh, well, maybe there was something else in the biology, and you go and study a 3rd neuron type and you connect it up in your network. But ultimately, the bigger issue is that your original fits they're not really designed to work together. So you came up with the most precise solution, but it's not the most appropriate solution to work in a network together with other neurons that have also been fitted. And I mean, I can't overemphasize that the requirement for expert knowledge in this is just huge. So, is there a solution? Maybe. So there's something known as hybrid approaches, and this is just coming. And from my perspective, I'm seeing it more in industry than I'm seeing it in academia, which is also quite interesting. So the example here is from a group spun out of the Charité here in Berlin. So they work at the Berlin Institute of Health, which is a sort of an incubator for the Charité and the MDC. And the projection is not so nice, but basically what they do is they have stroke patients, and you put the patient in an MRI when they arrive in the hospital. This is already done very rarely. This is not done on a wide scale. It's done at the Charité. It's not done in other hospitals. It's done in a handful of hospitals in Germany. But you get an image from them immediately. And there's 2 clinically relevant problems. One is you don't know when the stroke happened. And the other is that the drug that you give that may be able to treat stroke kills 15% of the people you give it to. So you have a really interesting issue of whether to give them the drug or not. Sounds like a classification problem, perhaps. And they have quite an interesting solution. So this drug needs to be given early. If it's 4 hours past the stroke, it's probably not worth giving it to them. It may be in certain cases. It's not been well enough studied. But from a safety point of view, because of that 15% mortality rate, usually the clinical standard is if it's more than 4 hours, don't give it to them. So what they're doing is they take the patient and they scan them immediately. And they also scan them a week later. And this right now is basically the training data. And some of those patients receive the medication and others do not. And I mean, that's all done on clinical basis. It's not done to get data points, okay, just to be clear. But how their model functions is quite interesting to me. So they do a structural scan of the brain, and they look at the structure of the vascularization, so where the blood vessels are. Because stroke is ultimately some kind of burst blood vessel. So it's a blockage or a burst, basically, and the blockage leads to a burst. And it's killing neurons around it. They're starving them of oxygen, and it's applying pressure, and basically they're dying. And you want to see, if we give the patient this particular drug, they already had their stroke at this point. It may be over by now, and a week from now, even if we don't give them the drug, they would be in the exact same state either way. But some of them could be helped a lot. And so the training data, or the system, looks at first this vascularization, and they do a simulation based on that. So they use that structure to predict the blood flow going through the different veins and arteries and so on, the blood vessels. But separately, they have a machine learning model. And this is looking at all of the clinical records of the data, of the patient. And it's looking at all of the measures you have, anything you can use to make a decision on. And it's being hooked up also to the MRI image, the actual imagery data, and then it's also being augmented with the simulation. So the simulation is coming out of the MRI data, but you would never have enough data points, enough MRIs to train a machine learning model to learn this kind of structural identification of blood flow. So they build it in instead, because we know roughly the physics of diffusion, and they simulate it. So they're putting in the physics at that point, and that's an input into the machine learning model. At the end of that, they combine all the data points, and they make a prediction of basically what kind of... How they do it is they divide up the brain into voxels, and they say, per voxel, if you give them the drug now, will this piece be saved or not from damage a week from now? So would it be damaged a week from now if you don't give them the drug, and will it be if you do give them the drug? And the doctor looks at a nice image and basically sees the two different comparison outputs and says, okay, for this patient, right now the damage is quite small, but a week from now it will be a whole hemisphere if I don't treat them, so I'm definitely going to give them the drug, I'll take the risk. But if it's going to be a no difference either way, then they don't give them the drug, is the idea. But the importance here from my modeling point of view is how they augmented the data set using known physics. So everything, I mean, it is roughly speaking a machine learning model. It's just that they built in some simulations behind the scenes to give you better data. So I've been kind of fast, slow? Okay, I think we have a few minutes. My clock is gone. So I just threw in one last slide because while the brain one was this other group, this is what I'm working on now. So, yeah, it's gone. I'm working on the immune system, and we're trying now to simulate the immune system. But it's never going to be one of these bespoke simulation models. We're instead trying to combine the two in a hybrid approach. So we're combining the bottom-up simulations with the data-driven approaches. And so that's what I'm working on at the moment. And I guess... Sorry, I kind of killed the ending there by talking about the clock. I'll finish there.
Do we have any questions? Hi. Thanks.
Yeah.
Very good talk. I have a question. How was the simulation added? I mean, is it a feature? Is it like, how does that work?
So, first of all, I don't work for the group. They were kind enough to share their image with me. But my understanding is, I mean, they're feeding in the raw MRI voxel data, and they're basically augmenting it per voxel with some kind of output from the simulation. So a diffusion measure, basically. And I don't know for definite, but I think it's about 6 data points per voxel. which are basically characteristics of diffusion at that local point.
And that is fed on top of the other features. That
Exactly.
Okay.
At the same time, a single classification. Yeah.
Okay, thanks.
Hi.
No. Yeah.
So thank you for a great presentation. In your experience, how does medicine look at models based on neural networks, taking into account that these are black boxes, so there's no full traceability in why a model takes a certain decision?
So that's kind of one of the things I want to get across in the talk, that computer-aided decision-making is not a problem, as long as you can present it like this stroke case where you show visually, best of our knowledge, our prediction is that in this voxel it's going to be damaged if you don't give them the drug, but if you do give them the drug, it won't. That one's okay because it's so far away from our biological understanding of the system. But and it's also giving them at least the illusion of power in the decision-making process. But no, in most cases there's a huge issue here. And I mean, personally, I don't trust black box models for most medical issues. I think they're classifiers, and if you can phrase it as a classification problem, then it's not a problem, and you should use these methods. But I mean, for most clinical decisions, it's not a classification decision. That's step one, and then there's a what do we do about it. And it's usually 100 classifications feeding into a decision process, and that's what a clinician is doing. So yeah.
So are you saying that if a system like this is part of a larger decision support process, then it should be fine? Something like that?
So, I mean, yes, for that example, for the stroke example, and for the pneumonia and so on, but could you automate away the imagery where you get rid of the radiographer? I would say someday probably, but right now, no way in hell, because these systems are being trained up individually. And so, I mean, if I need just a slightly different angle on my body, maybe I'm missing an arm and it just totally screws up the image or something of my chest. You need a human there to interpret that for now.
Right, great, thank you.
Thank you. Now there was one up the front. No, we need the audio for the video.
Yeah, thanks for a great talk. You referenced the talk on the respiratory machines there. The question of interpretability arose there as well. And one of the questions at the end had to do with using tree-like structures in the learning. And I'm wondering if you had an opinion on that.
I think they're cool. I like them. They lead a lot of data, though. So I think for the neonatal data, there's probably going to be enough data available, at least if you try. And I mean, so this is something that's not so well appreciated. I mean, there was the bad news about IBM recently that Watson may not be as good as they claimed, which was not a very well-kept secret. But decision systems for symptom-based classifiers for diagnosing patients, I recall reading that in the 90s they already surpassed clinicians. So, you know, computers are really good at some of this stuff. You just want a human there because there's so many other things. There's the human being who doesn't present things the same way because their husband beats them, you know, because there's something else in the data set that confound, basically. And the neonatals, it's not clear to me whether you can have enough data, but probably in that case you could because it's such simple data. But no, the trees are great, but just, I mean, it is really an issue of N here. Can you get enough data points? But in terms of being able to point at stuff, I think it's really useful, yeah.
Oh, thank you.
Beside you. He's
So just one last comment. It's like from our perspective as clinicians, I think it's almost like machine learning would help us to remove some of the primitive models we have. I think because in clinical care, most of us hold such a primitive models of coming from the 19th century, and we make our clinical decisions based on these models, and people will just stuck to it because that's what they learned, that's what they pass on. And I think we had some very nice examples. Like, have you heard of the Hero, which is a machine learning-based sepsis classifier, which is just looking at like heart rate variability, and it actually detects, predicts sepsis, whether the patient is septic or not, and it works better than the nurses. So there are, I think, some very new products here, and also programs which are developing.
So there was one down the bank left, but
All right.
yeah.
Thank you. Great talk. Thank you. Not necessarily a question, but maybe more as a comment that we were talking about pushing the end to the big, but this is also not necessarily a solution, because if you have a float way of collecting data, then you just reinforce your certainty in patterns being present in the data if you push the end to the to the big side. With big or small n, you should be trying to give the model your priors or the knowledge that you are certain about. So just as a comment, or maybe to make it a question, do you agree?
No, I agree. I think that's a good note to end it on.